My name is Pete Vukusic. I am a professor of physics at Exeter, and my research group studies the way in which colours are produced in natural systems, such as those of insects, birds, fish, and plants. I've been working in this area for around about 2 decades. Prior to that, I was a school teacher. I came back to Exeter, was in discussion with my PhD supervisor, Roy Sambles, and we spoke about what project I might do coming back, maybe as a postdoc. Roy happened to have a butterfly on his wall in a showcase, and this butterfly was a Morpho Butterfly, and it was gloriously blue. It's not an ordinary colour, it's a spectacular, brilliant colour. And we decided upon a project relating to trying to understand how the colour is produced in systems like these, in brilliant blue morphos, in fish scales, in bird feathers, in beetle elytra. These evolutionary processes that underpin the development of appearances like that don't happen by accident. The brilliant blue of Morpho has a very strong functional purpose, and that is for communication over very long distances. Very often it's the males of the species that are brilliantly coloured, and certainly in the case of the Morpho butterfly, the males are brilliantly blue because they tend to communicate to other males over long distances, effectively saying, don't come to my area, don't come to my hilltop, this is my courtship domain. And my brilliant colour is an indicator of how fit I am. So a Morpho butterfly is a relatively large butterfly in comparison to the UK species. There are 40 or so Morpho butterflies, and they're renowned for their blue colour. 200 and 300 years ago, zoologists travelling in the Amazon across South America brought them back to the UK to put in library and museum collections. Morpho butterflies are visible from around about a quarter of a mile away, and they can even be seen fluttering tops of trees in the forest canopy from low-flying aircraft. They are that brilliant. The way in which the colours are produced is really at the heart of our reason for studying them. If we can understand how such colour is produced in very ordinary materials, then we should be able to apply this understanding to future technology and developing technology. And that, indeed, has happened in several areas. The brilliant blue colour of the Morpho butterfly and the brilliant colours of many other plants and animals is described as a structural colour. In other words, it is not based on pigmentation, but it's based on the presence of microstructures, sometimes nanostructures, in the epidermis or on the plant or on the scales of the animal. And those microstructures interact with light in such a way that a portion of the visible spectrum is reflected strongly, blue, for instance, in the Morpho case, and the rest of the visible spectrum is not reflected, and usually it's absorbed in the body of the animal. The way in which this works relies upon the wave-like behaviour of light. So we know, and we're taught, and we can read that light can show wave-like properties and particle-like properties. So it can be a wave or it can be a particle, depending on the experiment we do. In the case of structural colour, we understand the mechanism to rely on the wave-like behaviour of light. So imagine that we have a thin film of soap solution, or a very thin film of glass, a millionth of a metre thick, let's say. Light waves of all colours fall upon the surface. Some portion of those light waves is reflected. The other portion, the remaining portion, is transmitted to the bottom surface of the film and that's then reflected upwards as well. So the way in which we tell whether a bright colour is reflected from that thin film, let's say, is to understand that if the peak of the wave reflected from the top surface overlies spatially with the peak of the wave reflected from the bottom surface, these two are going in the same direction, then those waves will reinforce each other, resulting in what we describe as constructive interference and a bright colour. If the peaks don't overlie, or rather if the peak of the reflection from the top surface overlies with the trough of a reflection from the bottom surface, then we refer to that as destructive interference. And in that case, no colour is reflected. So in such a case, let's say in a soap film or in a tiny thin film of oil on a puddle of water, or on a thin film of protein on the surface of an animal, the colour which is reflected explicitly depends on the material and on the thickness of the film. So in the case of the Morpho Butterfly, for example, we don't just have one layer, as we see is responsible for the colour in soap films. We have multiple layers stacked on top of each other. And it's the combined effect of all of those layers inducing constructive interference, bright reflection for blue, that gives rise to the intense, brilliant, iridescent blue reflection on Morpho's wing scales. When we first studied the Morpho, or decided to study the Morpho, we had to get some species. I was lucky enough to be allowed into the basements of the Natural History Museum in London, and they have tens of thousands, hundreds of thousands indeed, of species collected over the last 200 and 300 years. And they were remarkable. It was a moment, a visit that really changed my scientific direction completely, because of the amazement I felt when I saw those colours and I saw the species. When I got back to Exeter, we decided to do some experiments shining different coloured lasers and lights at the wings of these specimens. We had to find some specimens. And the easiest way, even 20 years ago, was to order online. And they came in two different ways. They came papered with wings closed, these butterflies, and one would then dissect the wings and use specific small regions of each wing, or they came pinned. The way in which we did our experiments involved using the pinned specimens, because straight out of the box, the brilliantly blue wings of these Morpho butterflies were visible, and we could put them on our kit and shine our lights at them and to do our spectroscopy and all the measurements that we needed. That was relatively straightforward, even though the experiments were pretty involved. I did try in the early days to open the papered specimens and go through the process that's described in all the books to reveal the colour of the dorsal side of these wings. But no matter how I tried to relax the wings as per the instructions and slowly to tease out the colour that lay beneath, I found it really challenging and never succeeded. My recommendation to any would-be collectors or enthusiasts or scientists who are looking to do experiments on these, go with the pinned specimens. It's the most straightforward. I wouldn't recommend the papered specimen approach.
Blue Morpho, Crypsis, Nymphalidae, Morphodidius. Against advice, you buy a papered Morpho butterfly. It comes by post in glassine, folded like a valentine. You observe its coiled proboscis its legs drawn in, its shut wings mottled brown, their stubborn crypsis. You make a crude relaxing box, chicken wire, sponges, naphthalene, then shut the lid. On the fourth day it is time. You lay it out and pry the wings apart, like peeling a steamed stamp off an envelope, to a sudden turquoise flash of iridescent bliss. You're afraid to tear its sky gleam silk. Your fingers stumble and trip. The wing's top hinges, supple, strong, resist, and the bright wings shut. Again you force them wide, breathing hard, as if to resuscitate a corpse. The wings begin to bruise and crush. Oil from your fingers rolls in tiny beads across their film. The stains proliferate and breed all your dirty human effluence. You become frustrated. Imagine weights to hang off the wingtips. Wonder what they could take, these fierce mechanisms that you still force back like a book whose spine you mean to break, brutish taxidermist in a mothball fug. Then, as you hold the right forewing between index finger and thumb, you feel a pulse, and a wild hope comes that the delicate pump that flushes the lymph to work the wings has woken, that the butterfly has woken, and you're overjoyed, as if in the wake of that resurrection you could shrink to an innocent. Hook your heels between forewing and aft, hold the pinions and ride as the Morpho flies south to the cloud forest, following its instinct, a blue evasion, its changing scattered flash. Everything in your muddied soul suddenly yearns to go, as if you were the victim needing to be delivered, not this butterfly, pinned and stained with all the greasy pressure of your hands, this bothered corpse. And then you know it for your own dull pulse, conduit through these wings, stimuli that fails and fails to start the murdered engine. All the while the pinions clap shut, resist your bullying attention, your tweezing and ineptitude and sweat. You imagined it would open like a flower in water, but now you're cursing like a body snatcher, trying to force a mortised jaw, bitch Narcissus, trying to find a poem in this butterfly's blue sheen, which you pretend you've brought to study, but you only covet. Its shiver at the blue end of the spectrum, its unseen violet, all the dead but shimmering electrics the butterfly has no need of now, but still protects. It closes its door, it closes its door, and there's no way back to innocence from here.